Hello, Mr. Betts here. Let's take a look at a few examples where we use the candidates test to determine absolute extrema. So the question here says determine the absolute extrema of the function on the closed interval. Remember, the extreme value theorem guarantees that if we have a continuous function, which any polynomial is going to be continuous on a closed interval, then we have to have an absolute maximum and we have to have an absolute minimum. So the process that we're going to take is to first identify the candidates. And I'm going to write out these steps as we go on the first one, and then I won't do that on any of the future ones. So we want to identify the candidates, and the two types of candidates that we're going to get are going to be critical values and also endpoints. Endpoints are easy. Those are right there. Critical values, we're actually going to take the derivative. So we need the derivative so we can figure out where that's equal to 0. And we set the derivative equal to 0. So to solve that, I'm going to factor out a 12x squared, and that leaves an x minus 1. And so we get critical values at x equals 0 and 1. I do want to point out that 0 and 1 are both on the interval, so we are going to use both of them. And our other candidates then are going to be those endpoints. So we have candidates at x equals 0 and 1 because they're the critical values, -1 and 2 because they're the endpoints. So remember, these candidates are the only x values where we could have the absolute maximum and we could have the absolute minimum. And we know that the absolute maximum and the absolute minimum occur because of the extreme value theorem. So putting those two things together, all we have to do is figure out what is the value of f at each of these points. So we're going to plug them in one at a time into the original function. Be careful you don't go into the derivative here because we are looking for the max and min of f. So the biggest value of f, the smallest value of f. F of 0 is pretty easy. That's just going to be 0. F of 1 is going to be 3 minus 4, which is -1. F of -1 is going to be 3 plus 4, which is 7. And f of 2 is going to be, this one's a little trickier, 48 minus 64. Nope, I did that wrong. 16. Okay, so those are the values of the function at the candidates. And remember, the maximum and minimum have to be in there somewhere. And if I were to graph these points, the -1 here is going to be the lowest point, and the 16 here is going to be the highest point. So those are going to be our two absolute extrema. So I'm going to write out my answer here, including all the information that I might need. Keep in mind that when we're doing problems, we want to make sure we answer the question specifically. As the question asks, just find the extrema. I don't know if that means X or Y, so I'm going to give both. So the absolute minimum, start with that. It doesn't really matter which one we do first. Value of f of x is, so the minimum value is the smallest value of the function itself. That's the y value. So that's going to be -1. And that occurs at x equals 1. Then on the other hand, for the max, we have the absolute max value of f of x is, so the maximum value is 16, which occurs at x equals 2. So notice that one of these is occurring at one of the interior points and one of them is occurring at one of the endpoints. If we actually look at the graph of this function, the candidates that I have highlighted here, the green ones because they're critical values and the blue ones because they're endpoints. And you can see here on the graph that this one is the minimum value. It's the lowest of all the points on f of x, and this is the biggest of all the points on f of x. So that's going to be our absolute max. So example 2 is really similar, just different function, different interval. So we're going to identify candidates by finding critical values. So we got our function is g. So g prime is going to be 2 minus 2/3 times 3 is 2x to the negative 1/3. And I want to know when that is either equal to 0 or undefined. So in order to do that, I'm going to rewrite this. So it's going to be 2 minus 2 over x to the 1/3. And it might be easier for our purposes. Well, no, we can go with this. So if this is equal to 0, that's going to be one of our critical value types. Then we get 2 minus 2 over x to the 1/3 is 0. I'm going to move this 2 to the other side by subtracting 2, and then I'm going to divide by negative 2. So I get 1 over x to the 1/3 is equal to 1. And then if I cross multiply, I get x to the 1/3 equals 1. And that's going to give me x equals 1. So that's going to be one of our critical values. That's when the derivative is equal to 0. Now, we're also going to get a point on this interval where the derivative is undefined. So the derivative is going to be undefined when the denominator here in our fraction is equal to 0. So x to the 1/3 equals 0, which is going to give us x equals 0. So we have a critical value here where the derivative equals 0. We have a critical value here where the derivative is undefined. And we also are going to have candidates at the two endpoints. So our candidates are x equals 0, x equals 1, x equals negative 1, and x equals 3. So 0 is where the derivative was undefined, 1 is where the derivative equals 0, negative 1 and 3 are where the endpoints are. So now what we want to do is find the value of the function at those points. So again, we know that the maximum or minimum is going to be at one of these points. We just need to know what the value of g is at the points so we can pick the highest and the lowest. So g of 0 is going to be 0 minus 0, which is 0. G of 1 is going to be 2 minus 3, which is negative 1. G of negative 1 is going to be negative 2 minus 3 times negative 1 to the 2/3. I'm writing this out because it's a little bit trickier. So this part of it right here, negative 1 to the 2/3, is negative 1 squared, which is 1. And then the cube root of that is 1. So it's going to be negative 2 minus 3, which is negative 5. And g of 3 is going to be negative, sorry, not negative, 6 minus 3 times 2 to the 2/3, which I'm going to go ahead and square it. So 3. Now, the cube root of 4, I don't know what that is, but I'm feeling like I made a mistake here. I plugged in the wrong number at the endpoint. That should be 3 to the 2/3. So this is going to be 9 to the 1/3. Sorry about that. Okay, so 9 to the 1/3, or the cube root of 9. I don't know what that is, but I do know it's greater than the cube root of 8, and I know the cube root of 8 is 2. So I know the cube root of 9 is greater than 2. I also know it's going to be just a little bit bigger than 2. So if we look at perfect cubes, we have 2 cubed is 8, and then 3 cubed is 27. So we are really close to the 2 cubed here. So when we take the cube root of 9, we're going to be really close to 2, but just a little bit bigger. So what that means is this is a little bit bigger than 6. And so we're going to have a number that is a little less than 0. And I know that's not very formal, but what I do know is that it's not going to be less than -5 for sure. And I also know it's not going to be greater than 0. So just narrowing it down to kind of a small range here, a little less than 0, now I can choose this 0 here as the max and the -5 as the min. So G has a global, or we could say absolute, min of -5 at x equals -1, and G has a global max of 0 at x equals 0. So again, we've got some other points here that are not maxima and minima, at least not global. They could be local extrema, but they are not global extrema. And indeed, if we look at the picture here, the candidates again are identified, the green as critical values and the blue as endpoints. And we can see that the lowest one on the graph is at -5, and the highest one on the graph is the one at 0. All right, let's do one more here just to get a little more practice, this one involving some trig. So same question, different function, different interval. We want to find absolute extrema. So we're going to start by taking the derivative. Derivative 2 sine of x is 2 cosine of x. Derivative of cosine of 2x, we're going to have to use the chain rule there. So we're going to end up multiplying by 2 because that's the derivative of 2x. And it's going to be negative sine, and the negatives multiply to get a positive. So it's going to be 2 sine of 2x. Now this one's going to be a little bit tricky because we need to we need to set this equal to 0. So I'm going to use an identity that you have seen before but probably don't have memorized, and that's okay. And that's the double angle identity for sine of 2x. Sine of 2x is going to be the same thing as 2 sine of x times cosine of x. Realistically, this question would be a calculator question on the AP test, and then you would be able to use your calculator to graph the derivative and figure out where it's 0. I want to do it analytically, so I'm pulling in this identity here. So by using that identity, we can think of the derivative now as 2 cosine of x plus 4 sine of x cosine of x. And by doing that, we can factor out a 2 cosine of x, and that leaves 1 plus 2 sine of x. And we do want to know when this is equal to 0. So the whole point of this is figuring out when this is equal to 0. And so we have 2 cosine of x equals 0, and we have 1 plus 2 sine of x equals 0. So cosine of x is going to equal 0 at pi over 2 and at 3 pi over 2. Then we're going to have sine of x equal to -1/2. So sine is equal to 1/2 for the pi over 6 degree angle. Sorry, I shouldn't say degree, pi over 6 radian angle. And so sine is going to equal -1/2 in the third and fourth quadrants. So that's going to be in the third quadrant, pi over 6 is going to be 7 pi over 6. And in the fourth quadrant, it's going to be 2 pi minus pi over 6, which is 11 pi over 6. So we have 4 critical values on the interior of the interval. And then we also have our endpoints that we need to consider. So we have candidates. We actually have 6 different candidates here. This is going to be fun. So candidates are going to be at x equals pi over 2, 3 pi over 2, 7 pi over 6, 11 pi over 6, 0, and 2 pi. So we need to find the value of h of x at each of these points. So we're going to just start plugging into the function. So h of, let's just go in order here, h of pi over 2. So remember, we're plugging into h of x here. So we have 2 sine of pi over 2 minus cosine of pi. Sine of pi over 2 is 1, so that's going to be 2, minus cosine of pi. Cosine of pi is negative 1, so that's going to give us 3. H of 3 pi over 2 is 2 sine 3 pi over 2 minus cosine of 3 pi. So sine of 3 pi over 2 is negative 1, so that's going to be negative 2. And then cosine of 3 pi is going to be, what's that going to be? That's going to be negative 1 also. So negative 2 minus negative 1 is going to give us negative 1. All right, next one. These are going to be the good ones here. 7 pi over 6. So we have 2 sine of 7 pi over 6 minus cosine of 7 pi over 3. All right, so sine of 7 pi over 6 is going to be negative 1/2. We figured that out down here. So this is going to be negative 1. And then cosine of 7 pi over 3 is going to be the same as cosine of, so that's the same as cosine of just pi over 3. So the same reference angle there. And cosine of pi over 3 is 1/2. So we have minus 1/2 is going to be negative 3/2. All right, then we have h of 11 pi over 6. So we have 2 sine of 11 pi over 6 minus cosine of 11 pi over 3. This is the same reference angle as 5 pi over 3, which is in the second quadrant. And cosine is negative in the second quadrant. So that one's going to give us a plus 1/2, I think. Let me think that through. So we're going to have 2 times negative 1/2 is going to be negative 1. And then cosine, I'm sorry, that's in the fourth quadrant. And cosine is positive in the fourth quadrant. Good thing I checked that. So it's going to be minus 1/2, so that's going to be negative 3/2 also. Okay, h of 0. This should be a pretty easy one. So we have 2 sine of 0 minus cosine of 0. Sine of 0 is 0, cosine of 0 is 1, so that's going to give us negative 1. And h of 2 pi. So sine of 2 pi is 0. Cosine of 4 pi is the same thing as cosine of 0, which is 1. So we have 0 minus 1 is negative 1. Okay, so the biggest value we have along here is 3. And the smallest value that we have here is going to be negative 3/2, and that happens in 2 different places. So the negative 3/2 is here and here. So we have not much room to write this. H has a max value of 3 at x equals pi over 2 and a min value of -3/2 at x equals 7 pi over 6, and that's not a 6, 11 pi over 6. Sorry, I squeezed that in there. So keep in mind this is a global max and global min. I didn't have the space to write it here. So this one's a little bit more intensive, but the process is the same. Find the critical values, test the critical values, test the endpoints, plug them into the original function. And with the trig here, this just got a little bit trickier with that. Be careful with that. So if we look at what this graph looks like, we've got our 4 critical values on the interior marked in green, and then our endpoints marked in blue. So our minimum values were here, and our maximum value is there.